Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now, in the previous sections, we just talked about how the operating system keeps track of all free spaces, known as the holes, using a linked list. And we also talk about the different search strategies, like the first fit, next fit, best fit, and the worst fit. Now, we actually find out that using these memory management, there's an issue of the external fragmentation, which results in the loss of usable memory space. So, in this section, section 6.3, we're going to talk about the other approach. That's called paging. So we're going to use the paging to actually solve the issues of external fragmentation. So the main disadvantage of dividing memory into variable partitions is external fragmentation, which requires the searching of memory for holes large enough to satisfy each request. Now, external fragmentation will eventually result in the loss of usable memory space. Now, there are two options people can use to resolve the external fragmentation. One is the swapping. The other one is compaction. We just discussed this in the previous section, right? Now, these two approaches are necessary when no holes large enough is available. So, but it's also very costly. So then people think about the other ways to resolve this external fragmentation. One solution is the paging. Okay, so paging divides both the logical address space. Remember, we have a logical address space, before we actually load the computer program into the memory, and then we have physical address space, right? So the paging divides both the logical address space of a process and the physical memory into contiguous equal-sized partitions. So then, for example, they divide the equal-sized partitions. It's the partitions of the same size, and then we also partition the physical memory of the same size. Now, each partition is called a paging, and the corresponding partition in the memory is called a frame. Okay, it's called pages, frames. Okay. So when we actually load the program into the physical memory, instead of actually find a hole that put the whole process into the physical memory, we just match the pages. So let's see if this program requires, for example, 4 pages. Okay, and then we just need to find 4 friends in the physical memory and fit each page into a frame. Now the good thing is with the paging, you don't have to find all 4 friends in the contiguous memory location. So these 4 friends could be scattered all over the places in the physical memory. So in order to map the page into frames, you don't have to actually map all 4 pages into the same location in the physical memory. So this may resolve the issues of external fragmentation. So let's first talk about some of the terminologies used in paging. Now first, a page is a fixed size contiguous block of logical address space. Okay, suppose I have a logical address space here. Okay, so then we have a logical address, okay, 1, 0, 1, 2, and all the way to something like n minus 1. Okay, that's a logical address space. Now, page is the fixed size contiguous block, okay, of a logical address space. Now, the block size varies depending on the user. You can define a block of, say, 10 words, okay. So that means you're going to take like a 10 logical address from 0 to 1 to all the way to 9. So we can define this as a page. Okay, and then we can define another page from logical address 10 to 19. Also contains 10 words. Okay, and then from 20 to 29, that's another page. Okay, so that we can define all this, and then eventually we're going to have enough page to cover the whole logical address. But the last page may not exactly match the leftover memory addresses, right? So sometimes it may be actually a bit bigger than the leftover of memory addresses. Okay, so that's the last page. Okay, also supposedly contains 10 words. Okay, even some of the space are wasted. That's the space that's wasted. Okay, now suppose that we have, so the first page in this logical memory address is called page number 0. And the second one is page number 1 and 2. And that all the way saying, let's say page number m minus 1. So that means, so instead of measure the logical memory space using the number of words, which is n, so the size of this is n words, and then we actually measure this using the number of pages. In this case, we have m pages, right? From 0 to n minus 1. Okay, so now a page frame is a fixed size contiguous block of physical memory identified by the single numbers, the page frame number, or sometimes we simply call the frame number. So then for the physical memory, we're going to divide the physical memory into the page frame. Okay, now the page frame size should be the same as the page size, the size of page. So if the page use 10 words, that means it could take 10 logical memory address. Then the page frame also going to take 10 physical memory address. So let's say starting from 0 to 9. So that's the page frame, and that's page frame number 0. And then 10 to 19, that's page frame number 1. 20 to 29, that's page frame number 2. That we can actually go all the way, and then we can define, the page. So if we can actually create the memory such that the memory eventually gonna have the page frame number, let's say k minus 1. So that memory contains k page frames. Okay. So now, what is page table? The page table is an array that keeps track of which pages of given logical address space reside in which page frames. Because if the program is in the logical memory space, measured in using the pages. Now for this example, the program takes m pages, right? So that's the size of the program. Now we no longer measure the program using the number of words or number of logical memory space, we use the page number, okay, the number of pages. So now, then, if we want to load this program, into the memory, okay, all we need to do is we need to find m page frames. Okay, so the memory size is k page frame. So k is probably a bigger number, but m is definitely going to be smaller than k. So in order to actually allocate the memory space for this program, which use m pages, then all we need to do is we find m page frames and match each of the page into one of the frame. Okay. So for example, if this frame number 1 is available, so we can match, let me use different color. Okay. So we can map page number 0 to frame number 1. And you can map page number 1 to one of the frame over here. Let's say frame number 7, okay? And then you can map page number 2 to another frame. Okay. So as far as we find m page frames, now you map all m pages into the m page frames, then we complete the loading of the program, right? And the good news is that these m frames doesn't have to be in the same memory location. It could be scattered all over the places. Okay. Now, in order for the operating system to keep track these which pages in which frame, because operating system need to know eventually which page is loaded into which frame. Okay. Now, that the page table is basically designed to keep this mapping. Okay. So here, then the page table contains, let's say, the page number, and then the frame number or page frame number, right? So let's say, what's the page 0? Page 0 going to map, in this case, page 0 map to frame number 1, page 1 map to frame number 7, page 2 map to whatever the frame, I don't know, but so for each of the page from 0, 1, 2, 3 all the way to the last page, page n-1, gonna map to whatever the frame we can find in the physical memory space. Now that's the page table. Okay. So it's an array that keeps track of which pages of a given logic address space reside in which page frame. Okay. Which pages reside in which page frames. Okay, so that's the purpose for the page table. So without a paging, each process is measured in terms of the number of words or number of addresses. So before the loading, the process is measured in terms of the logical address space. For example, the process is going to be actually start from logical address 0 all the way to 100. So now with paging, the process is measured in terms of the number of pages. So for example, in this case, the process 1 has 3 pages, page number 0, 1, and 2. And the process 2 actually measured as 2 pages. Okay. So also, the physical memory is also partitioned in terms of the page frame. Each page frame has the same size as a page. So now, in order to accommodate the process 1, all we need to figure out is, do I have 3 page frames to accommodate the process 1? Or do I have three actually free friends. Okay. And then I find out, okay, friend number 0 is free, friend number 1 is free, and friend number 6 is free. So I actually, load page number 0 to friend number 0, load page number 1 to friend number 1, and the friend number 2 is not available. So I then find out friend number 6 is available. So I load page number 2 to friend number 6. Now for page number 2, I map, load page number 0 for process 2 to friend number 2, page number 1 to friend number 4. So now once we actually done the mapping, so we need to record this, right? The operating system need to keep track of these, mapping, make sure that which pages, which process is actually loaded into which page frames. So that's why the page table is actually introduced. So in this case, the first column represents the page number, as I mentioned in the previous slide. And then this is actually the page frame. Page PT1 is a page frame number. So 0 maps to page frame number 0, 1 maps to 1, and 2 maps to 6. And in this case, 0 maps to 2, 1 maps to 4. Okay, so that's the page table. So we're going to discuss this in much detail. Okay. Okay, so let's talk about the pages in much detail and relate the logical and physical addresses with pages and page frames. Now in this example here, so we have a physical memory, and the size of physical memory is 64 words. So that means we need a 64 physical address, and each address can represent the location of a word. So the address starting from 0 and all the way to 63, right? Now let's see, with 64 addresses, how many bits do I need? In another word, how many bits do I need to represent 64 different numbers from 0 to 63? Now, if you remember, 64 is actually power of 2, which is actually the same as 2 to the 6. Okay, if you're familiar with the binary numbers. Okay, so with 2 to the 6, so that means 64, for 64 numbers from 0 to 63, I can use 6 bits to represent the 64 different numbers, starting from 0 all the way to 63. Now, in this here, you can see the, we have 66 bits. Okay. Now, the decimal number 0 can be represented by 0, 0, 0, 0, 0, 0. Okay. Now 1, I can represent using 0, 0, 0, 0, 0, 1. And 2, it's a 0, 0, 0, 0, 1, 0. So I basically, with 6 bits, I can represent a decimal number from 0 all the way to 63. 63 is all 1. Okay. So we can randomly pick a number, say like a 0, 0, 0, 1, 1, 1. That's 7, right? Because 1, 1, 1 in binary, it's 7. And a 1, 1, 1, 1, 4, 1, that's 15. Okay. So I can use 60 bits to represent 64 different memory address, the physical memory address. Okay. Now, for the logical space, if I have a program, so the program actually takes, for example, like a 32 words, let's say. Okay, so that means I have a program, and once the program is created, then I have a process which we put, the size of the process is 32 words. Okay, now with 32 words, I need a 32 logical address space, right? So from 0 to 31. Now, if you remember, 32 is 2 to the 5. So if you're still familiar with the binary number, you will find out that I can use 5 bits. Okay, I can use 5 bits to represent 32 different numbers from 0 to 31. Now here, if you look at this side, you can see that I have a 5 bits. Okay, so the first one's 0 represent the logic address 0, and 1, 2, 3, and if we're going down, the last one is 1, 1, 1, 1, 1, 5 ones. That represents 31. Again, that's 15. Okay, so I use dot 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 because I don't have enough space to write all these 31 different numbers. Okay, so that's 7, right? So that's the logical memory space. Now, if I try to load this process of 32 words into the physical memory, then without a paging, I need to find a 62 contiguous memory location, or a hole of 62 memory address. So then I can load the whole 62 actually, process into the memory location. That's kind of difficult, right? Because if we don't have any holes of 64 words, then you cannot load the program from the logical address space into the physical memory. Now, with paging, so let's introduce the paging. So let's see, I'm going to divide the logical address into a block of fixed size. Okay, let's first say I want to, divide the logical address into a block. Each block contains 8 addresses. Let's say, so 0, 1, 2, 3, 4, 5, 6, 7. From 0 to 7, that's 8, right? So if I divide logical address into 8, and then here's another one. So from 8 all the way to 15, that's another 8. Okay, and then I can divide another 8, and the then last one is also contains 8, addresses. Now I define this as a page. Okay. Now what's the page size? The page contains 8 memory address, or the logical memory address, right? And this is another page. So basically I can call this page, the first page is called the page 0, and that's page 1. And what's the last page? Also contains 8. Now it's easy to calculate, right? Because we have total of 32 words, and each page contains 8 words. 8 words, okay? 8 address. So 32 divided by 8, it's 4. So that means I can divide 32 words into 4 pages. Each page contains 8 words or 8 memory addresses. So the first page is page 0, second page is page 1, and third page is page 2, and the fourth page, the last page, is page number 3, right? So basically, I can divide it into 4 pages, and each page has its own, has 8 memory addresses. Okay, so now I can just say that's the, okay, number of, that's one page. Now that's the second page, right? Okay. Now, what about if I partition the logical address into a different, the blocks of different size? Let's say I partition the logical address into, a block of 4 words, a block of 4 words, a block of 4 words, block of 4 words, and a block of 4 words. Okay. Now, each 4 words actually makes a page. So I can say this is page 0. That's page 1. That's page 2. Page 3. Now what's the last page? How many pages we're going to have? So now this time I have 32 words, and then each page contains 4 words. So then I can just get the 4 times 8 is 32. So I got the 8. So that means I'm going to have 8 pages. If the page size reduced from 8 words to 4 words, then the number of pages actually becomes 8. So if I use the numbers to represent the page number, the first one is 0, the last one going to be 7, right? So I have a page 1 to 7. Okay. So this is going to be 1 page. Okay. Now, if I actually partition the logical address space into a page of size 8, then I have to partition the corresponding physical memory address of 8 word, and I call this page frame, right? Now make sure if the logical memory space use the page of 8 words, and then the physical memory space is going to use the page frame of 8 words. Okay. So that's the thing. Now suppose I use the page size 4. Okay, page size 4. Say the logical actually, the physical frame going to be divided into the size of 4 as well. And that's the frame number 0. That's frame number 1. And that's frame number 2, 3, 4. And how many frames do I need? How many frames that do I have in this case? Now, remember the frame size is 64 words, right? Now, the frames, the memory size is 64 words. The frame size is 4. Okay, so if I divide 64 by 4, I got 1, 4, 24, 4 times 6, 24. So I have a 16. So that means I have a 16 page frames. So starting from 0, so the last frame number going to be 15, right? From 0 to 15, that's total 16. Okay, so that's the frame size. And I normally call this like a page 0. No, page 0, page 1, page 2, page 3, and the last one is page 7. And the friend is friend 0, friend number 1, friend number 2, friend number 3, and friend number 4. The last one is friend number 15, right? So that's a friend. Okay, now to accommodate the programs in a logical space for this, in this case, the size of the program in the logical space is 8. Now, if I want to accommodate this thing, all I need is to find 8 frames in the physical memory, 8 free frames. Right? Now, for example, if friend number 1 is available, let's say friend number 1 is available, so then I can load page number 0 to friend number 0. Okay. And then I can load another frame, page, another page 1 to another frame. So as far as I can find 8 frames, 8 free frames in the physical memory, then I can accommodate, the process with 8 pages. Now let's talk about this, the relationship between the frame number and also the page address. So you will realize that if for friend number 0, okay, so I have a total number of 15 friends, or actually 16 friends, right? Now for 16 friends, remember 16 is how many bits do I need to represent 16 different numbers, 16 friends from 0 to 15. Again, 16 is 2 to the 4th. So the power of 4, that's the number of bits do I need to represent 16 different numbers. Okay. So now for friend number 0, so the number, let me actually erase some of this so I can free up the space here. Now, let's see. So, okay, so now, let's see, I have 16 friends, right, in this case. So which means I need 4 bits to represent 16 different friend numbers. 0, 0, 0, 0, that represents 0. 0, 0, 0, 1 represent 1, 0, 0, 1, 0 that represent 2, and then and for last one, 1, 1, 1 that represent 15. Okay, so that I need 4 bits. Now, if you actually notice this memory address, so basically you can figure out that the first 4 bits over here in each frame are all the same. For frame number 0, F0, the first 4 bits are all 0. Now for frame number 1, the first 4 bits 0, 0, 0, 1 are all 1, right? And then for frame number 2, the first 4 bits are 0, 0, 1, 0. That's 2, right? Now look at the last one, frame number 15. So the first 4 bits is 1, 1, 1, 1. Basically, it represents the number 15. So technically, when I actually divide the memory address into frames, then I actually divide memory address into 2 parts. Okay, So I can use the first 4 bits in this case to represent friend numbers. Now, what is this the remaining 2 bits? It's always start from 00011011, 00100111. So now these are called offsets. The number of offsets basically represent the location of this number in this particular frame. For example, 01 basically means, okay, it's in the second position because the first position is 00, second position is 01, and third position is 10, and the fourth position is 11. Okay, again, 00 means the first position in frame number 1, and 01, 10, 11. So these are called offset. Okay, now same thing, I can do this with the logical memory space. Remember, logical memory space, the total is 32 words, right, for this particular case. And so there are 8 pages, page 0 to page 8, right, page 7. So the page number is page 0 to page 7. So the total number of pages is 8. Okay, now for 8, how many bits do I need to represent 8 different page number from 0 to 7? 3 bits, right? So now we can find out. So the first page 0, I can use the first 3 bits. They're all the same to represent the page number. And that's page number 1. That's page number 2. And that's page number 3. And the last one is page number 7. So the first 3 bits represent a page number. And the remaining 2 bits are the offset. Okay. So now we realize that because the physical memory is much bigger than the logical memory, so the physical memory memory address is longer. In this case, requires 6 bits, okay, to represent. But the logical memory space only contains 32 words, so I just need a 32 memory address. So I just need 5 bits to represent. Okay. Now, if I partition the page and the frame into the same size, now you will realize that both have the same offset. Okay, so the offset takes 2 bits. Offset takes 2 bits. Now for 2 bits, you can represent, 4 different numbers. So that means offset basically means the number of address in each of the pages or each of the frames, because the page and the frame has the same size in this case. So then we can allocate each page to a frame. Another page I can allocate to another frame, right? So this part, the first part, represent the page number. Okay, and also the first part here represent the frame number, the page frame number. Okay, and also the second part represent the offset. Offset. So what's so good about this? So then when we build a page table, now how can we build a page table? Okay, so we can build a page table. Let's see. Let me actually erase this one again, so I don't need that information, temporary information. So let's say if I have a mapping of the page to pages to the friends. Now, how can I build a page table? Okay, so I can build a page table like this, page table. So let me actually use different color for the page table. Let's use red color. So in the page table, so I map the page number 0, the first page, to friend number 1, right? So here's a page. Here's a friend number. Now page number 1, in this case, maps to friend number 3, right? 2, 3, 4, 5, 6, 7. So now page number 2, I don't know which friend number page number 2 going to map to. Okay, I don't know. But once we actually, maps the page number 2, to a friend number, I can update the page table. So make sure each page can map to something. Now, for example, the last page, page 7, maps to, let's say I can map the last page to friend number 4. So page 7 gonna map to friend number 4, right? And page 6, I don't know. Depend on which one maps to which. Okay, so I can build a page table to basically record which page maps to which friend numbers. Okay, now with the page table, then I can do the memory binding. Eventually, we want to, the paging is just a tool. So eventually, we want to make sure if I want to execute any instruction in a particular logical memory address, I need to know which physical memory address this logical memory address is mapped to, right? With pages pages not enough. Okay, now let's see. Let's take a look at this example. Let's say I use a purple color. Say I want to know what this logical memory address going to map to the physical. Okay. So when I look at the logical address, logical memory address 00010, right? So then I look at the first 3 bits. It's all 0. So I know that's page 0, right? That's page number. That's offset. So the page is 0. So then, what is this page mapped to? So then I look at the page table, and I find out page number 0 maps to friend number 1. Okay, so page number 0 maps to friend number 1. So it maps to this friend. Okay, so page number 0 maps to friend number 1 because friend use 4 bits. Okay. Now, what is the memory? What is the physical memory address this logical memory mapped to? So it's pretty simple. So once I map the page 000 to 00001, then for the offset, I just need to copy the offset. So it's a 10, so I just say 10. Now that's the physical memory address that this logical memory address is mapped to. Now what is this in here? So once I actually say, oh, okay, this maps to friend number 1, And then I just need to say, okay, the offset is 10, right? So then I just say, okay, here's the offset. So this is going to map to this address. Okay. So remember, the offset is just tells the relative position of this particular address in this frame. So the position is number 3. So 1, 2, 3 is number 3. So it's a number 3. The position never changes, okay, in the page or in the frame. So this is the mapping, the actual mapping of the address. So from the discussion in the previous slide, we know that for each of the logical memory space, if the logical memory space has n words, and now we assume that the n equals 2 to the n, right? So n equals, the capital N equals 2 to the n, then we know that so the n words, if you can use n bits to represent the whole, address from 0 to n minus 1, right? Now, so when the address space is partitioned into pages, the page size is of the form 2 to the k. So that means we use k bits to represent the offset, which also represent the page size, okay, the size of the page. And then, because total, the logical memory address is use n bits, so that leaves the high order bits like n minus k, right? Now that n minus k space represent the page number. Okay. Now for the physical memory, so if the physical memory contains m words, okay, now m equals 2 to the m, the capital M equals 2 to the m, so the physical memory use m bits, right? Now, if we want to make sure the paging is working, then you have to make sure the frame size is the same as page size. So that means the offset also going to be k bits. Okay. It should be the same as the logical address. So this leaves the frame number area, the size of m minus k, right? So that could be m minus k could be bigger than n minus k if the physical memory is bigger than the logical memory. Okay. So now we know with paging, a logic address is broken into 2 components. Okay. Now here's logic address. We broke it into 2 components. One is the page. The other one is the offset. We use W to represent offset. Okay. So that's logic. And so that's logic address. Now the physical address is also broken into 2 components. And the first part is a frame. The second part is offset. Remember, the offset should be the same size. And so here's a frame. Okay. Now in the previous example, the page number can be represented using 3 bits, right? The frame number used 4 bits. Okay. So if in a page table, like a page number 0, 0, 0, 0, maps to frame number 0001, then we can do this mapping accordingly. So the page actually, page 00 maps to frame 111, and then the offset, if the memory address in page 0 is actually 00001, then when we map the page to the frame and we just copy 01, just copy the offset, and then that's the mapping of logic address to the physical address. The logic address is this, 5 bits. The physical address is 6 bits, 000101. Okay. Now this diagrams give you the summary of what we are talking about. So I have a physical memory here, and that's the logical memory space. So the page number 0, P0 maps to F frame number 1, and P3 maps to frame number 15. So in the page table, I can actually page 0, which is all 0, maps to frame number 1, it's 0001. And then the actual memory depends on the offset. Okay, so if the offset is XY, it will map, so the logical memory address 000XY maps to 0001XY. X could be 0 or 1, or Y could be 0 or 1, which represent the different offset value. Okay, now for another mapping like page 3, so I say, okay, page 3, that's 0, 1, 1, that's page 3, maps to frame number 15, 1, 1, 1, 1, right? So then I could get basically 0, 1, 1, 0, 1, 1, XY, if that's the address, any address in page number 3 maps to the frame number 15. So it's 111XY. So whatever the value for X, whether it's 1 or 0, whether it's for X, or whether it's 1 or 0 for Y, you're going to basically copy the offset. So the mapping is pretty straightforward. Once you got the page table, maps the page to a frame, so then the corresponding logic address can be mapped to the corresponding physical address. Okay, now here's this diagram basically shows you this. If P maps to the frame number F, then the offset should be simply copied. Okay, so that's the page table. P maps to F, so then so it could be mapped to F0 all the way to F to W. So each, depend on the offset. Every actual offset here maps to the same offset here. Okay. Another example. Let's see. Page 0 maps to frame number 0. So that means, page 0 maps to frame number, page 0 maps to frame number 1. And the page 3 maps to frame number 11. And the page 1, 2, 4, 5, 6, 7, I don't know. I just put the asterisks, means that I don't know which one is mapped to. Now, suppose I map page 1 to frame number 3. Okay, and then I update this page number 1, and I update this one to frame number 3. That's 0, 0, 1, 1. Okay, so the page table should reflect this change, if I map P1 to F3. Okay, so then that means XY gonna map to 3, that's 0, 0, 1, 1, x, y, right? We should reflect that change. Okay. So that means the logic address 0010, 0010. First, we look at the page table. 00 maps to 0001. Okay. So this is a map to this. And then the offset is 10. So then I just simply put the offset over here. So this one gonna map to this address. So it's pretty straightforward, right? Yeah, it just map to this. So now, using the paging, we can map a program that takes certain number of pages into the memory. Okay, we don't need to check the holes. Make sure there's a big hole to accommodate the programs. All we need to do is, I need to measure the size of the program, the process. If the process actually takes four pages, and then all I need to do is find 4 frames in the physical memory. And that 4 frames doesn't have to be in the same location. It could be scattered all over the places. So I just map each of this page to a different frame in different location. Now operating system just need to keep the page table, make sure which page maps to which frames. So this actually avoid the external fragmentation, right? The page actually avoid the external fragmentation by having all pages and all frames the same size, so that any page fits into any frame without creating holes between frames. Okay, now external fragmentation has been avoided. However, there's another issue. Now using paging, we're going to create another kind of fragmentation. It's called internal fragmentation. What is internal fragmentation? Let's see. Suppose I have a process. Okay. The process is going to take, the size of the process is going to take a logical space from 0 to, logical memory address to, let's say, 20. Okay. So this process takes like a 21 logical address or 21 words. Now, if I use the paging, let's say I use the paging, the page size is 4. Okay, so the page size is 4. So then I can partition this program from 0 to 3, and so that's 4, 4, 4, 4, 4, and 4. So each page takes 4 memory address. So I have a 4, 4, 4, 4, 4. I have 5 4s. That's total of 20. Because it's from 0 to 20, it's 21 address. So then with 5 pages, page 0, page 1, page 2, page 3, page 4, I have 5 pages. These 5 pages are going to actually cover total of 20, logical address, memory address. And I have still 20, right? So that means the last 120 is the 21st memory address, because remember it's starting from 0. Okay, so then this first one covers the logical address from 0 to 3, and 4 to 7, and 8 to 11, and 12 to 12, 13, 14, 15, and 16 to 19. Okay, So for memory address 20, logical memory address 20, it's not included in any of the pages. Now what I'm going to do? So I need to add another page. Okay, that's page number 5. So I actually need 6 pages to cover the memories from 0 to 21. Now for this last page, only one address is used. Now the other 3 memory logic address is empty. Now that's the wasted space. Okay. Now this wasted space is called internal fragmentation. So internal fragmentation is the loss of usable memory space due to the mismatch between the page size and the size of the program. Now, if the size of program is just a multiple of page size, that's perfect match. But most likely, the size of program is not exactly match. So the last page may only cover part of the memory address, the logic address. Okay, so then there's a wasted space over there. So that's called internal fragmentation. But internal fragmentation is really not really that big compared with the external fragmentation, right? Thank you.